Okay, so today we're going to talk about continuous random variables. And the nice thing about this is that it's just an instant replay of discrete random variables. There's a few differences, and so I'll go over those differences, but it's pretty much kind of a little like a review for you. Nothing bad. So with that, I should be able to go forward. Come on. Okay, first, what's it all about? We're going to do so we're going to do a little review of continuous random variables, and then we're going to figure out how to calculate probability for continuous random process, and we're also going to consider how to determine properties random processes such as the expected value and the variance. And so with that, I should be able to get just as a reminder, recall that random variables are functions that assign a numerical value to every event in a sample space. So possibilities include things like fuel usage. That could actually, it's not a discrete value of 1 gallon, 2 gallons, or whatever. It can be 1.1111. And also parts from CNC machines, that again could be many different values. In general, for any continuous random variable x, we can use the sample space that's given by minus infinity to plus infinity, where that sample space contains all the real numbers. And we can have a cumulative distribution function that's very much like the cumulative distribution function for discrete random variables. And that is, you can see right here, there's the cumulative distribution function is the summation of all those probabilities that are less than whatever your given value is. A probability density function is given by the derivative of the cumulative distribution function. So you've probably seen these ideas. Here's the derivative right here is just the slope of that line. So then we can see that that derivative, that slope, becomes the new value for the distribution function. So what is a PDF, or probability density function, good for? Note that for any values, A is less than or equal to B, we can say that all we need to do is integrate that probability density function, and we can actually find a probability of something happening between whatever those two numbers are, A and B. Also, what we're really doing is we're integrating, or actually we're taking the derivative of the cumulative distribution function. And if we wanted to, we could find the same probability by simply subtracting cumulative distribution function values between, for example, B and A. So the properties of a probability density function, well, they're actually pretty obvious. Since the cumulative distribution function is monotonically increasing, we would have that this probability density function is greater than 0 for, well, every place it exists. And it's going to be piecewise continuous. That's the usual rules. And integrated over the entire sample space S, we would have that. You integrate this, everything under that, f of x, whatever it is, this area has got to be 1. So let's look now at this continuous random variable, and we can say that x can assume values between x is equal to 1 and x is equal to 3, and we've got a density function right here, defined right here, So show that the area under the curve is equal to 1. Okay, so what that means is you're going to be integrating this. So integrate it and then find the probability that x is between 2 and 2.5. And it probably will be something less than 1. Okay, so in working this problem then, for A, show that the area under the curve is equal to 1. So what we'll do is we'll say that area is equal to the integration from 1 to 3 of 1/2 times dx. Okay, so if we're integrating a constant, that just means take that constant times x, right? So we'll just bring x in there and then evaluate it between 3 and 1. So it'll be 3 2's minus 1 2. And voila, that does turn out to be 1. And so it is a probability density function. So part B, find the probability between these two areas. Well, that's pretty simple. We're just going to, okay, we know what the whole area is, it's 1. So we're going to find, obviously, some kind of fraction of that. Let's take a quick look at what we're doing. We've got, we're going between 1 and 3, and there's 2 if you're interested. Okay, so we're going between that. Now, this whole area is 1. We're now being asked to evaluate between 2 and 2.5. Well, I mean, if I could draw better anyway, you can pretty clearly see that that should end up being about 1/4 of the area. So, indeed, if we integrate from 2 to 2.5 of 1/2 dx is equal to 1/2 times x, evaluated from 2.5 to, and so that just ends up being x, well, essentially, well, you can do that in your head, but it equals 1/4 by the time you're done. So, so that's for part B. Now, here's a tricky part. Let's say that I had asked you for a part C that would be the probability that x is less than or equal to 1.6. Now, if you were to do that, there's a way I mean, this is set up to trick you. How am I trying to trick you?
Do it from like use the second equation and put 1 to 1.6.
That's it. Okay, so you may not know, but Ricky just answered it in the back of the room. Okay, so we're not going to integrate from 0 here. We're going to integrate from 1 because look, there's nothing here at 0. We have to start at 1. And indeed, so we're going to integrate from 1 to 1.6 x, sorry, 1/2 dx. And if we take that all out, it's equal to 1/2, 1.6, 1 is equal to, x is equal to 1.6 over 2 minus 1 over 2, and all of that turns out to be 0.3. So that's the only real tricky one is this one right here, and you just have to remember where the edges are. That's why I always like to draw if I can draw. Okay, and now what we have now is a comparison of discrete versus continuous functions. And discrete functions, you can see they're very discrete, they're self-satisfied and smug. So here's the individual little discrete ones, and you add them all up between A and B in order to find out what a probability is. Now for a continuous random variable, you don't add things up. You integrate, okay? So you just integrate between these two values. Now, here's where I want you to look at the difference. If you look at this edge, you add that when you're adding the probabilities, right? You'll be adding this portion and these portions. But look at this one. At the very edge, where the probability distribution function is at A or at B, do you include those values?
Yes.
No.
Because those are equal to, so you included
It says it, but you can if you want to, but you don't have to. Why is that? Because look, this area, hopefully, this right here, whoop, I'm not drawing it very well. How thick is that A? You try doing this. So. How thick is that A? It's infinitely thin. And so if that area is sort of the dx, this little dx, I'm going to draw this, let's magnify it. It's actually this dx and whatever the height of fx is at that point. So these multiplied together give you the area of this little strip. But look, that dx is, we let the x go to 0, the dx go to 0. So it has no area. So that's why it doesn't matter whether it says less than or equal to or just less than, it's still the same. So that's pretty much what we've got right here. It's showing that the probability, if we're inspecting exactly at a point A, for example, we roll a dice and we want to know what the probability is that we're going to roll a 2. So we'll roll a 2 and it has a certain probability, right? 1/6. But here, what is the probability that it will land precisely on A? Precisely. Ain't going to happen. No matter what you do, you're not going to get exactly.
The picnic near the lakeside in Chicago was the start of a lazy afternoon, early one October. We begin with a scene 1 meter wide, which we view from just 1 meter away. Now every 10 seconds we will look from 10 times farther away, and our field of view will be 10 times wider. This square is 10 meters wide, and in 10 seconds the next square will be 10 times as wide. Our picture will center on the picnickers, even after they've been lost to sight. 100 meters wide. The distance a man can run in 10 seconds. Cars crowd the highway. Powerboats lie at their docks. The colorful bleachers are Soldiers Field. This square is 1 kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. We see the great city on the lake shore. 10 to the 4th meters, 10 kilometers. The distance a supersonic airplane can travel in 10 seconds. We see first the rounded end of Lake Michigan, then the whole Great Lake. 10 to the 5th meters. The distance an orbiting satellite covers in 10 seconds. Long parades of clouds. The day's weather in the Middle West. 10 to the 6th, a 1 with 6 zeros, 1,000,000 meters. Soon the Earth will show as a solid sphere. We are able to see the whole Earth now, just over a minute along the journey. The Earth diminishes into the distance, but those background stars are so much farther away that they do not yet appear to move. A line extends at the true speed of light. In 1 second, it half crosses the tilted orbit of the moon. Now we mark a small part of the path in which the Earth moves about the Sun. Now the orbital paths of the neighbor planets, Venus and Mars, then Mercury. Entering our field of view is the glowing center of our solar system, the Sun, followed by the massive outer planets, swinging wide in their big orbits. That odd orbit belongs to Pluto. A fringe of a myriad comets too faint to see completes the solar system. Ten to the 14th. As the solar system shrinks to one bright point in the distance, our sun is plainly now only one among the stars. Looking back from here, we know 4 southern constellations, still much as they appear from the far side of the Earth. This square is 10 to the 16th meters, 1 light year, not yet out to the next star. Our last 10-second step took us 10 light years further. The next will be 100. Our perspective changes so much in each step now that even the background stars will appear to converge. At last we pass the bright star Arcturus and some stars of the Dipper. Normal but quite unfamiliar stars and clouds of gas surround us as we traverse the Milky Way galaxy. Giant steps carry us into the outskirts of the galaxy. And as we pull away, we begin to see the great flat spiral facing us. The time and path we chose to leave Chicago has brought us out of the galaxy along a course nearly perpendicular to its disk. The 2 little satellite galaxies of our own are the clouds of Magellan. 10 to the 22nd power, 1,000,000 light years. Groups of galaxies bring a new level of structure to the scene. Glowing points are no longer single stars, but whole galaxies of stars seen as one. We pass the big Virgo cluster of galaxies among many others, 100 million light years out. As we approach the limit of our vision, we pause to start back home. This lonely scene, the galaxies like dust, is what most of space looks like. This emptiness is normal. The richness of our own neighborhood is the exception. The trip back to the picnic on the lakefront will be a sped-up version, reducing the distance to the Earth's surface by 1 power of 10 every 2 seconds. In each 2 seconds, we will appear to cover 90% of the remaining distance back to Earth. Notice the alternation between great activity and relative inactivity, a rhythm that will continue all the way into our next goal, a proton in the nucleus of a carbon atom beneath the skin on the hand of the sleeping man at the picnic. To the 9th meters, 10 to the 8th, 7, 6, 5, 4, 3, 2, 1. We are back at our starting point. We slow up at 1 meter, 10 to the 0 power. Now we reduce the distance to our final destination by 90% every 10 seconds. Each step much smaller than the one before. At 10 to the minus 2, 1/100th of a meter, 1 centimeter, we approach the surface of the hand. In a few seconds, we'll be entering the skin, crossing layer after layer from the outermost dead cells into a tiny blood vessel within. Skin layers vanish in turn. An outer layer of cells, felty collagen. The capillary containing red blood cells and a roughly lymphocyte. we enter the white cell. Among its vital organelles, the porous wall of the cell nucleus appears. The nucleus within holds the heredity of the man in the coiled coils of DNA. As we close in, we come to the double helix itself, a molecule like a long twisted ladder whose rungs of paired bases spell out twice, in an alphabet of 4 letters, the words of the powerful genetic message. At the atomic scale, the interplay of form and motion becomes more visible. We focus on one commonplace group of 3 hydrogen atoms bonded by electrical forces to a carbon atom. 4 electrons make up the outer shell of the carbon itself. They appear in quantum motion as a swarm of shimmering points. At 10 to the minus 10 meters, 1 angstrom, we find ourselves right among those outer electrons. Now we come upon the 2 inner electrons held in a tighter swarm. As we draw toward the atom's attracting center, we enter upon a vast inner space. At last, the carbon nucleus. So massive and so small. This carbon nucleus is made up of 6 protons and 6 neutrons. We are in the domain of universal modules. There are protons and neutrons in every nucleus, electrons in every atom, atoms bonded into every molecule out to the farthest galaxy. As a single proton fills our scene, we reach the edge of present understanding. Are these some quarks at intense interaction? Our journey has taken us through 40 powers of 10. If now the field is 1 unit, then when we saw many clusters of galaxies together, it was 10 to the 40th, or 1 and 40 zeros.
Between A and A, there's no area there. There's nothing there. We can never get like exactly on to a particular space. So this is actually a very important concept, and that is that the probability density function, this f of x, is a measure of the density of probability in a region, but it is not a probability function. So look, this is a density function. This is a probability. Don't be sure not to confuse the two of them. So for those of you who haven't, or maybe it's been a while since you've seen integration and derivatives and so forth, I thought that I'd do just a quick review. Newsflash, I am my own mother function claims. E is a number whose value is about 2.72. It's used as a base, as we know. The function e to the x has this amazing property that the derivative is the function itself. So it's sort of like giving birth to yourself. And if you've given birth at all, you know that that would be a totally amazing. I have no idea how hard this is to do with. Okay, so watch this. We're going to take here, the slope here is m, and the actual value is this green line. So now you can see how, just what the slope looks like. So we're just plotting out the derivatives there. And now we're going to just plot out another derivative. So there comes our derivative. And we're just moving right along, or at least we should be. Okay. So now we want to, let's see, want to get e to the x. Oh, well, this is cool. Let's use this. So there we go. Okay, so we're going to go to a user defined, and that will be e x graph. Okay, now we're going to take the derivative here. Watch this. Look at this. At every point, the derivative is itself, which I think is just really cool. So there you go. Okay, so an example, just a reminder example, is find the derivative of e to the sine x, and we would use the chain rule to differentiate here. So and you'll see these kinds of things, so this is a good reminder for you. Derivative of e to the sine x is just e to the sine x and then times the derivative of what was upstairs, which is cosine x. So it's just going to be e to the sine x times cosine x. Now, since the derivative of e to the x is just e to the x, we know immediately that the integral of e to the x is just going to be e to the x plus some c. So if e to the x is its own mother, then it's its own child, and we probably mutilated that particular analogy as far as we possibly can. So we can find a lot of other integrals using substitution. So for example, and this you will see, so make sure that you remember how to do this. If you have something like e to the 3x and you are integrating it, I've seen this so many times that I know that whatever is right here, you just move downstairs plus a constant. But if you want to really beat it to death, you know that you can just assign a variable u to be the equivalent of 3x. Then the derivative of u is just 3 dx, which means that we can rearrange and say du over 3 is equal to dx. Then we can substitute and say e to the u, and then we have to write dx there, right? But dx is just du over 3 from here. Now we integrate and we find, well, golly, it's e to the u over 3 plus c, and that is, when you substitute, e to the 3x over 3 plus a constant. So that's how we got that. Okay, so more generally, it's worth remembering that whatever's here just goes downstairs when you integrate, plus the constant. So now, based on extensive testing, we find this particular problem. And so what I would like you to do is work this problem. Now, one thing I want you to notice is it says, based on extensive testing, it's determined that the time y in years before a major repair is required is characterized by this. So integrating from 0 to whatever the time is, that's the probability that, well, this is the probability density function. So integrating it will give you the actual probability of that a major repair would be required by the time it hits that end point. For A, notice that what we're looking for is that the product's considered a bargain if it is unlikely to require a major repair before the 6th year. That means it breaks after year 6. So what we want to do is get the probability that it breaks somewhere before the end of year 6, and then what we want to do is take 1 minus that, and that's going to be the probability that it breaks after year 6, right, or whatever that little point is at the very beginning of year 6. So if we take this value right here and we're going to integrate it, 1/4 e to the minus y over 4, and we're going to integrate from 0 to 6 dy, we'll have e to the minus y, and we have a 4 upstairs, oops, and a 4 downstairs, so those cancel. Evaluated 6, 0, and so that's going to be e to the minus 6 over 4. Oops, I forgot to put the minus sign right there. So there's our minus sign. So there's a minus sign there, and then minus minus makes it plus e to the 0. So all of this becomes 1 minus e to the minus 6 over 4. That's this part. It's this part right here. So we have to take 1 minus this value. 1 minus e to the minus 6 over 4. And that is just e to the minus 6 over 4. And that's your probability that it's going to break after year 6. So now what is the probability that a major repair occurs sometime during the first year? So for this case, we're going to have the probability that y is less than or equal to 1. So we're going to have this is integration from 0 to 1, e to the minus y over 4 dy, and that is just going to be equal to 1 minus e to the minus 1/4, and that turns out to be 0.2212, and that's, let's see, this value means like there's a 20% chance that you're going to get a breakdown in the first year. Would you buy that washing machine? I wouldn't. And this one actually turns out to be, if you calculate it out, it's 0.2231, and that's actually not that small either, so I would not buy this washing machine. So there. Okay, now on we go. So expected value. The expected value of a continuous random variable x is given by, well, now remember before when we were calculating expected value for discrete functions, we took x, f of x, whoops, and we summed it up over all the x's, and that's how we found the expected value. This is very much like that. We're taking the x at that particular point times the probability distribution function, and if you recall, the following properties will hold. We've got the expected value. Any constant times x is just going to be the expected value times that constant, and then you can pull any other constant right out. One thing to be aware of is the expected value of a function is not the same as the function of the expected value. This may well be a constant, so the function operating on that constant is going to be different. So for variance, this is one of those things that should feel kind of familiar. Just to calculate the variance, it's take the difference from the mean at every little point, integrate it all up and square it, or the square of that, times the function itself. This is an alternative function that can be pretty handy. And we recall for the variance that actually it turns out to be squared inside. So what I want you to do is go ahead and take a look at this problem and see if you can solve it. Resume, and all we have to do is take this function and we're going to integrate. Let's see, we're going to take x times 2 times 1 minus x dx, and we're going to integrate, let's see, the average profit per vehicle. So here's the integration interval, so it's going to be 0 to 1, and we'll just say multiplying this all out, we're going to have, let's see, 2x minus x squared. And we're going to evaluate this whole business between 1 and 0. Dx. Did I miss something? Yes, I did. Thank you for that loud whisper. That was very helpful. Okay, so we'll pull that outside, and we'll say x minus x squared integral. Sorry, this is really unclear. 0 to 1 dx. So now we'll do the integration, and it's going to be 2, and then this will be x squared over 2, and then minus x to the third over 3, and this whole thing is evaluated between 1 and 0. And now we can just plug in numbers. So we're going to have 2 times 1 over 2 minus 1 over 3 minus 2 times 0 over 2 minus 0 over 3. So we'll just ignore that whole part. And now we have 1 minus 2/3. And that becomes 1/3. So is that the answer? It's almost the answer. Yeah, they want us to find the average profit per vehicle. So we found it's 1/3 of the units, which is 5,000. So it's going to be 1/3 times 5,000, and that is 1,000. Come on, 1,001 or 667.67, and that's what we've got. So now, what is the dealer's average profit per vehicle if the profit on each vehicle is given by this value? So we're actually sneaking you close towards something. So go ahead and work this. It's really similar to what we just did. So going back into action here. Now they're saying we've got this is the function. So what we're going to have to do is clearly take 2, and I'm going to put the x squared right on the inside there so we can see it more clearly. And so we've got this times dx, and then integrating from 0 to 1. And so now what we do is 2 out x squared minus 2x to the third, and integrating all of that from 0 to 1 dx. So then we can say x to the third over 3 minus x to the fourth over 4, 1, 0, and that becomes 2/3 minus 1/2, and then we're subtracting off 0, 0. So the answer is 2/3 minus 1/2, which is 1/6, and so we'll take 1/6 times 5,000, and there we go. It's $833.33. Heading on down, we have a continuous random variable x with a density function given by e to the x. Very handy because it's easy to integrate. Find the expected value of that function. So what we're going to do is we're going to take g of x times f of x and then integrate it over the entire range. So that just means we take e to the x, and this is really important. So make sure that you know how to do this. It's super easy, and in fact it's so easy it's perfect for tests. So then so that's g of x is 2/3 x. F of x is e to the minus x, 0, infinity, dx. So then how you do this is when you have e to the something or other times e to the something or other, you just add whatever's in the exponent. So then we can say that is equal to e to the 2/3 x minus x, and all of that is integrated 0 to infinity dx. So now we can simplify this. Look, 2/3 x minus x is just 1/3 x. So x over 3. And integrating 0 to infinity dx. Oh, well that's not too bad. Remember, whatever is in this exponent, you put it downstairs, minus the x, right, of course. So we're going to say e to the minus x over 3, and integrating it, well, let's see, minus 1/3, that actually comes upstairs, right? That's the same as 1 over 3 downstairs, and we've got that minus sign. And integrating from 0 to infinity. So if we plug in at infinity, what happens to the e to the minus x over 3? It goes to very small value, which is might as well be 0. And when we plug 0 in here, we get minus 3. So we end up with 3. And that, folks, is the expected value of g of x. So on a laboratory assignment, if the equipment is working, the density function is given by this, and what we're supposed to do is find the variance and standard deviation of x. If you go back and look at the formulas, you'll see we just got a lot of these values. So you can calculate this very, very easily. So go back, look at those formulas, and then you'll see quickly how to do that calculation. Let's go ahead and work this problem. So we've got the expected value, and we've already worked this, so I'm not going to beat it to death, is just 2, 0, 1, x times 1 minus x dx, and working that out, we get 1/3. And then the expected value of e to the x squared, yeah, I mean, let's see, just writing it out really quick but not working it, because we already did that, and that's 1/6. So then the variance is just 1/6 minus, well, 1/3 squared. So that will be 1/9, and that's 1/18 altogether. And the standard deviation is going to be the square root of that value, and that becomes 0.2357. Oh, that's my horrific way of attempting to draw sigma. Oh, sure. Make fun of my horrific penmanship. Okay, so now we're back to doing continuous probability distributions. And what we'll do is categorize several different kinds of continuous random processes and develop some of the probability formulas for them. So the first one is a uniform distribution, and it has a probability density function given by this sort of ugly looking equation. You might ask yourself, why do we have this 1 over b minus a? And what that is saying is, if you have a uniform distribution, here's your b, here's your a. This area here always has to be equal to 1. So that means when you're integrating from between a and b of whatever that value is, you've got to have a 1 over b minus a sort of as a constant multiplying it, because then when you integrate, or it should be 1, when you integrate, it will turn out to be 1 underneath here. That's where this factor comes from. So this is valid even if we interchange the strict inequalities. You know, so it can be either greater than or less than, or greater than or equal to, or less than or equal to. So it's pretty much why we would think, kind of beaten that idea to death. Where does this formula come from? I just sort of gave you that idea. Basically, you're integrating a constant between two values, and so here's b, here's a. So you have to have a constant that's 1 over b minus a, otherwise this will not end up being 1. So again, this is just a nice visualization of this whole process. And there's 1 over b minus a is the height of this. And let's see. If we want to integrate, and I think this is valuable to look at, if our whole probability is given by the area under this line, then a partial probability, when we're integrating parts of it, is just a fraction of the whole of this whole area. And so it's really nothing magical. We're simply taking this constant, 1 over b minus a, and then integrating to get the fractional percentage of the whole area. So notice that for any continuous random variable, and not just a uniform continuous random variable, we have notice this is less than or equal to. Here one of the equal to has dropped out. Here the other equal to has dropped out. And here both of them have dropped out. But that's okay. They're all the same. And you can see down here, in essence, if you're integrating over an area that is from A to A, there just ain't going to be no area there. So it's okay. The cumulative distribution function is simply given by this type of function right here, and the expected value and the variance are given by these, and your book again has a very nice derivation of these values, but you can just plug them in if you want to. So now let's go to another distribution, which is the exponential distribution, and that has a Poisson parameter. Okay, so we have the lambda, and it has we've got a continuous random variable, and we can have a time, and that time, that can be the time or the space between successive occurrences of a Poisson process. And we can have a probability density function given by this little rascal. And why do we have that lambda in front of it? Simple, because if we don't, then when we start trying to integrate, it actually won't integrate to 1 over the entire range. So that's why we need that lambda. The same Poisson process as in a Poisson distribution. Oh, sometimes depending on the book, you may have lambda is equal to 1 over beta. So if you see beta or lambda, just be aware that's the relationship between them. And for the exponential distribution, our cumulative distribution function is just the integration, and so it's 1 minus e to the minus lambda t, less than or equal to 0. That 1 comes from the integration starting from 0. And the expected value and the variance are just given by these formulas. Here's a little sample plot of a exponential distribution. So we've got here's our probability density function that's in red. As we integrate it, we've got this blue, and so you can see that as we integrate and we get more and more of the function sort of less than, you get closer and closer to 1. So exponential distribution versus Poisson is, here we go, there's the differences, there's exponential, there's Poisson, and the similarities are that we have a random process undergoing all of this. Lambda represents an average number of events, and the differences are that in Poisson, we're interested in a random variable that's discrete, and in exponential, we're interested in a random variable that's continuous. But the random process underlying all this is the same for both. I think that's really an important finding. So again, exponential distribution versus Poisson. Consider the previous network logon process that we had. If we have a Poisson distribution with a discrete random variable, what we're interested in is the number of logons during the selected time period. So that's going to be discrete. Otherwise, if we're looking at Poisson, we're interested in when the logins will occur. And that's an exponential distribution with continuous random variable. It's when it will occur, so it's not this sort of digital thing, the number of logins.